question 11 from the GATE 2018 EC paper, where we are given a 4x4 real matrix M and 3 statements S1, S2 and S3 for it, and asked to find out which of the following statements implies which of them. Underneath the question, you will find the title of the NPTEL course or video relevant to this topic.
So in this question, we are given that M is a real 4x4 matrix and M has the following 4 statements associated with it. We would like to know which of the statements imply which of them. That is it true that if M has 4 linearly independent vectors, that means M must have 4 distinct eigenvalues? It's not necessary that this is true. For example, the matrix I, right? So we are investigating whether S1 is true or not. So it's not necessary that. So for example, let's say that we take the matrix I, which is just 4 ones. It's a 4x4 matrix. So you will have to fill zeros in these locations, right? So the identity matrix, this has 4 linearly independent eigenvectors, that is the columns 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. These are all eigenvectors of I. Why? Because I into x is equal to x for all of these vectors, right? And that's just the property of the identity matrix. But as you can see, the identity matrix has 4 ones in its diagonal, or alternatively you can see that from here the eigenvalue lambda, so if Ax is equal to lambda x, then lambda is the eigenvalue for if x is not equal to 0. Right, so in this case x is not equal to 0, Ix is equal to 1 into x, so lambda is equal to 1. So having 4 linearly independent eigenvectors doesn't mean you will have 4 distinct eigenvalues, right? In this case all the eigenvalues are 1, so this is false. Next, let's look at if S1 implies S3, that is having 4 linearly independent eigenvectors, does it mean that M is non-singular? It's again not necessary. Let's consider the same I matrix, except I'm going to just turn the last element off. I'm just going to turn the last diagonal, main diagonal element as 0. Same thing, you'll have to populate zeros like so, right? And this matrix is not invertible because you have a column of zeros here. It's not invertible, but it does have 4 linearly independent eigenvectors. So the first 3 columns are the first 3 eigenvectors, and you can take any vector of the type 0 0 0 x. You just put anything for x, right? And if I call this matrix A into x will be, A into x will be equal to 0 into x. So the eigenvalue will be 0. Let's say for example, if I chose 1 for that, then it will simply extract A into that vector. A into this will be simply the fourth column. As you can see, it will only, if you do the matrix vector multiplication, you will see that only the 4th column will get pulled out, and this is of course equal to 0 into this thing. So this is an eigenvector with eigenvalue 0. So clearly A is not invertible, but it also has 4 linearly independent eigenvectors. So B is not true. Now the option C is true, and for that you can find a proof here. So the option C, it says S2 implies S1, that is, if M has 4 distinct eigenvalues, M has 4 linearly independent eigenvectors. And the reason that is true is because of this statement, which is that eigenvectors corresponding to distinct eigenvalues must be linearly independent. What does this mean? If Ax is equal to, or if Ax1 is equal to lambda x1 and Ax2 is equal to lambda 2x2, then, and of course if x1 and x2 are neither equal to 0, then if the eigenvalues are distinct, that is, the eigenvalues are not equal to each other, then it must be the case that the eigenvectors corresponding to those eigenvalues must be linearly independent, right? So that's what this says. M, if it has 4 distinct eigenvalues, then M has 4 linearly independent eigenvectors. You can of course pause the screen at this point and go through the proof of this fact, which is given here. So of course the answer is C, right? And D, which is S3 implies S2, right? S3 implies S2, which says if M is non-singular, that is, if M is invertible, then M has 4 distinct eigenvalues. Again, the example of the identity matrix, the identity matrix is invertible, that is, I inverse is equal to I, but as we have seen, all the eigenvalues are equal to 1 for the identity matrix. So therefore S3 is also not true. Thus the correct answer to this question is option C.